So yeah, this meeting is being recorded. Okay, yes, that's fine.
Okay, well, let's get going. I'm very pleased to welcome Dr. Benne Holwerda from University of Louisville to give us a talk today on, it's a bit of a 2-for-1, search for high redshift galaxies and an accidental galactic survey of dwarf stars. So Benne, originally he got his master's degree from Groningen University in 2000. After that, he worked for a few years at Space Telescope with Ron Allen before going back to Groningen and getting his PhD in 2005. After this, he did a number of postdocs, including Space Telescope, University of Cape Town in South Africa, one as a research fellow at the European Space Agency, before doing a final position at Leiden University before taking up his current position as associate professor at University of Louisville in 2017. So Benne, thank you very much for your time and for sharing some of your work with us. With that, I'll let you take it away.
Great. So yeah, I'll talk about two completely different projects, yet they're linked very intimately by the data itself, but the topics are essentially as far apart as you can almost be in galactic astronomy. And so I've done this with a varied group of people over the years. Joanna Bridge was my postdoc here at U of L. Michele Trenti is the PI of the data, some of the data. Stephanie Bernard is a student. Richard Bowens was my boss in Leiden, and Redske was a student. Isabel and Duartier were two undergrad students, and I'll talk about their project at the end of this. And the rest of the Borg team, this is a varied and very very active team, so I need to say thanks to their tireless effort to generate this wonderful data. If you want to contact me later, there's my email, and obviously I spent way too much time on the Bird app, so you can also find me there. So I'll start with the first one, the search for high redshift galaxies. So this is a tale of two topics. The first one is bright redshift 8 galaxies, and so that's the nominal target for the observations. And then the second one is mapping the brown red dwarf population of the Milky Way, which is what you end up accidentally doing anyway. So this basically starts as the Milky Way. That's the thing that I'm going to talk about later. And first we're going to talk about anything not the Milky Way, the extragalactic part. That was the slide that I put in to explain to my physics colleagues, because it's a physics and astronomy department here. And so the super 8s is the thing that I will talk about first, which is the massive galaxies of redshift 8. So these are the ones that the Borg survey targeted, and these are my collaborators in this first part. Redshift 8 is interesting for the following reason. We have the Big Bang, which is interesting and very eventful. Then there is a boring bit where there's just hydrogen floating around, and then at some point stars form and you get reionization. And so the height of reionization is right about redshift 8 or so. And that's why we're looking for the bright galaxies that are probably responsible for that. And I personally think everything else after that is also still interesting. Too many interests, it might be the subtitle for this talk. And so, let's see if this starts playing. Yes. So what we think is happening is that as the dark matter has these first potential wells, the gas flows into it, and the very first stars switch on. They overproduce or produce a lot of UV and start reionizing the hydrogen in the universe. And so this is a kind of important event, and we would like to understand better why, how it's happening, what are the responsible sources, and can we say more about the physical conditions in these galaxies at that time? So it's a pivotal time. You want to know what galaxies are responsible for it. And so we go look for these redshift 8 galaxies, and this is now a small industry with using the Hubble Deep Observations. These are all the filters from blue to red, all the filters that you can use with Wide Field Camera 3. And so as you redshift towards redshift 8, essentially you drop out of all the optical filters and only galaxies detected in the infrared filters. So the quickest and the cheapest way to find redshift 8 galaxies is simply take observations in a wide as possible optical band, optical filter. So we used 606 for the first instances of the Borg fields. And then the Y band to see if there's like a half a detection there, and then take 2 infrared bands to get a solid detection of this galaxy. And then you can characterize the galaxy in these two redder bands. And the non-detection in the optical really nails the redshift redshift 8 identification. So we've been looking for this Lyman break technique has been used very much in every deep HST field, and also lots of ground-based observations. So what we really are looking for is that getting to redshift 8 being right at the moment of reionization. So that's what we're aiming for. This is essentially starting in the 90s. We got depending on this. So this is all depending on having good infrared data. And so we're mostly talking about infrared imaging here. And even in 1995, the Hubble Deep Field, that was still all optical because the Wide Field Camera 3 wasn't installed yet. And so ACS was installed. It was sensitive to a little further, thanks to its red sensitivity, and only when the Wide Field Camera 3 was installed in 2010, you could actually get to just about redshift 10 using this technique. Of course, any talk about high redshift isn't complete without saying the James Webb Space Telescope 3 times, and so that's obviously the next thing that we're hoping for, and that will extend the technique all the way into redshift 20. So right when we think the very first stars switch on, and so that's our ultimate goal. But first, you want to, if you want to understand the reionization sources, you need to find enough of them, and those can be good targets for James Webb follow-up. So as an efficient way to cover a lot of ground, essentially, you can switch on the Wide Field Camera 3 while Hubble spectrograph is doing something else. So essentially, with COS, you're looking at a quasar, you're looking at an interesting galactic star, you're looking at something, and at the same time, you switch on the Wide Field Camera 3 camera. And we've got these 4 filters, so you make sure that you've got an optical filter and 3 infrared filters looking for those redshift 8 dropouts. And so the neat thing about this is that you get a random sampling across the sky. As you can see here, you don't get to say where you're looking, but a random sampling is fantastic if you want to do a shallow survey. It is much more robust as trying to do a degree's worth just consecutively. So multiple lines of sight, this tests really well against cosmic variance, for example. Because these are shallow observations, typically only 2 to 4 orbits, you're only sensitive to the brightest end of the redshift 8 distribution. But the good news is that that's the part that you're interested in. That's what you need to cover a lot of volume for. And for things like the candle survey over Hubble Deep Field, those are pencil beam, so they are sensitive to cosmic variance. And so this is a good way to check against that. So it's a very clever technique. I also feel the need to explain what I say when I'm talking about a redshift 8 galaxy. Typically, we think about, the Milky Way or the Magellanic Clouds as galaxies. In this case, I think of 30 Doradus on steroids. That's basically what we're looking at. Star formation-wise, just the size-wise, it's about a kiloparsec across. So these galaxies are basically this, I think. This is the picture in my head when I'm talking or when I'm thinking about redshift 8 galaxy. So really just a loose star formation region floating on its own. And so there's the technique that we do is we use the Hubble 4 fields to identify a high redshift galaxy candidate, and then we use deep Spitzer observations to actually confirm that these things that were actually high redshift galaxies. So to take 2 more points at redder wavelengths to make sure that they are proper high redshift galaxies. And this is explained here. So these photo Z's without Spitzer conformation, you can still have the blue. Is my there. So the redshift 5 dusty dwarf. So you can actually have a small galaxy that has a fair bit of dust in it at a much lower redshift, and its photometry will fit the 4 bands, the 4 HST bands in green pretty well. And so, especially if a little bit of photometric errors, then you can basically fool yourself that this redshift 5 dusty dwarf galaxy is in fact a redshift 8 super 8 bright galaxy. And so if you get Spitzer data, either in the 3.6 or 4.5 micron, or preferably both, then you can confirm with the red points that yes, in fact, it is a flat distribution, and that's in fact a high redshift galaxy and not redshift 5, which, you know, high redshift community thinks now redshift 5 is low redshift, which is a bit of a shift of nomenclature. And so your solution suddenly pivots to the orange line at the right here, and so yes, it's right at redshift 7.5, or, you know, close to redshift 8. The funny thing is that another good fit can be, for instance, a T0 brown dwarf in our own Milky Way. It's not even a galaxy, but it's also a small red fuzzy thing that also has a very similar colors for the kind of objects you can select. So we have two kinds of interlopers, and we have to correct for those, and Spitzer is the thing to use in this case. So having a far infrared photometry point suddenly clicks the photometric redshifts into unambiguous territory. The second thing is that if you have both filters in Spitzer, that the Spitzer color itself is actually very sensitive to the emission lines, the nebular emission lines of oxygen and H beta. And so these things are supposed to be booming with star formation, so lots of nebular lines. And Renske Smit in 2014 did this exercise, which is basically what is the Spitzer color as I shift everything to higher redshift. And so starting at redshift 7 and sort of ending at redshift 9, you get these weird IRAC colors. And so if you get both filters, you can actually see if there's a high equivalent with emission line. Now these are nominal. This is basically a flat spectrum with an emission line stuck in. How that exactly looks depends very much on the model. I'll talk about that in a little bit. But it is at least interesting to see that you can confirm that these galaxies are not only at high redshift, that you only need one Spitzer filter for that. But if you use both of them, you can see if they are currently booming with a nebular emission. So that was the idea that Guido Roberts Borsani pursued in 2015. He found 4 really bright, so 25.5 apparent magnitude is bright for high redshift galaxies. That means that their absolute magnitude is minus 22. They were all in the extended cross strip, and they were Spitzer red. And so they were about a magnitude above what you would expect for galaxies at this redshift, and they were all this Spitzer red color. And the interesting thing was, can we then see the glowing shell of Lyman alpha emission around these newly formed or very star-forming galaxies? And so that was the next target on our list, to go see if we could see the emission from the ionizing shell around these galaxies. And the interesting thing is that if you go look for Lyman alpha emission and high redshift galaxies, you are fairly successful out to redshift 6 and a bit, and then it sort of crashes, because then there is no Lyman alpha penetrating, because essentially the universe hasn't completely reionized yet. So you're in the process. So that's where reionization is happening. So you don't expect to see a lot of Lyman alpha emission from these galaxies, and that seems to be borne out. But the interesting thing is that in these super 8s, in these bright galaxies, we found, or basically these 4 authors found, Lyman alpha at the correct redshift. So the neat thing is here now that we have a spectroscopic redshift for these galaxies, And we have a predictor for how to find those galaxies at redshift 8 that do in fact have Lyman alpha emission associated with it. This is the shell around it, by the way, so it's not from the galaxy itself, and so there might be a few hundred kilometers a second of separation between the galaxy and the emission line. But that's an unusually good detection rate for redshift 8, right? So this is another plot of like how fraction of Lyman alpha, and then basically we have a 4 out of 4 detection rate for these. But they are only in the Groth strip. So the strong optical emission, as indicated by the Spitzer color, predict a Lyman alpha detection at redshift 8. So that would be an efficient way of finding just those galaxies that have already a bubble of Lyman alpha, or already a bubble of reionization around them, right at the peak of reionization. So that's interesting. So that way, at redshift 8, we can find those bubbles. So that would be a good, almost first galaxies. So we have a few questions, right? First is Lyman alpha emitters. Are they only in the extended Groth strip? It always makes me it makes the hairs on the back of my head stand up when you find your special source only in one of the 5 fields that you've looked at, right? If they're all 4 of them are in one, if all your eggs are in one basket, maybe there is some sort of bias that you were unaware of. So let's check with the Borg identified bright super 8s and Spitzer follow-up and follow them up and see if we can also see Lyman alpha. And so the last question is like, well, can you do this to even further? Like this Spitzer colorite trick works to redshift 9. So could we actually find Lyman alpha emitters out to redshift 9? And so that's what the current iterations of the Borg survey is basically doing. They're trying to find targets for redshift 9 to 10 bright galaxies. So these are the 2 follow-up that we started working on. And so first we do is get HST and Spitzer time to confirm these bright galaxies, ZS8 galaxies that we found in the shallowest of Borg fields. They are in 8 other random lines of sight. So if this is a kind of a typical phenomenon, not just limited to the Groth strip, then we can double our sample, which is, if you start at 4, that's still pretty good. We can go find if these are in fact super 8s, if they are confirmed at redshift 8, and then we can go see if they have Lyman alpha emission. So these are at the very brightest end of the luminosity function at this redshift. So they also constrain where the luminosity function at this redshift cuts off. And you'll find that in any high redshift survey, the bright end is actually very uncertain because it's typically constrained by 1 or 2 galaxies. So if you have more on the bright end, from shallow surveys, then you can constrain the shape of the luminosity function better. So that is what Joanna did. She has identified, well, she confirmed all 7 out of the 8 redshift 8 galaxies candidates that with Spitzer photometry, they are in fact at redshift 8. Some of them, the photo Z's are incredibly good. So having just that 1 extra photometry point already helped, and sometimes we had 2, depending a little bit on how deep the Spitzer data went. And so we have a couple of redshift and even 1 redshift 9 galaxies. So that's great. That constrains the luminosity function a little better. This agrees with existing other work using Hubble fields, and so we're all pretty happy that these are in fact redshift 8 bright galaxies. So the Spitzer confirmed that these are 7 and discounted 1, so we now have 11 super 8s. Unfortunately, there is no way that we can confirm things with Spitzer anymore, so there's no HST Spitzer teamwork happening anywhere more. So how do we select any new ones? Because if we, a sample of 11 is good, but to call it statistical is a little bit less so. And so if you want to come up with some targets for, say, James Webb or the future ALTs, that not only do you just use the colors for them, but maybe there are some other pieces of information that we can use. And so first we can actually push this with Hubble all the way out to JH, using JH and H. That's the reddest filter we've got. And so there are still some Redshift 9, 10 galaxies being selected by, oh, that was a little too quick, by the board team. This is ongoing. They're hard to confirm, especially because now we don't have Spitzer anymore. So you only have one photometry point for it and one bare detection, and then everything else is non-detection. So as you can see, they suffer a little bit from that. So we have how can we confirm without Spitzer? That's really the trick. There's two things that we can try. We can try sizes. Do these things conform to the size one would expect at Redshift 8 galaxies? And the neat thing is that size evolves a little bit different with Redshift in cosmology than luminosity distances. So we actually, Redshift's on our side there, so we can still resolve these galaxies at Redshift 8, and we will continue to resolve these things with HST. That's not the problem. And the other one is morphometrics. Are there some other qualifications that we can use other than they look fuzzy? So a big step in the selection of high redshift sources often is we inspect the HST image and do they look okay? And a visual inspection is incredibly powerful. I will not be somebody to knock that, but I'd rather have some kind of qualified quantification, especially if we are going from just a few HST fields to, Euclid, for example. So visual inspection, the size of morphometrics. So we have, for a typical galaxy, for a Super 8, we have 1, 2, 3, 4, 5 photometry points. So a sixth piece of information is already, is improving your knowledge of this galaxy. The half-light radius is a typical thing that you then do. And so looking at half-light radii for these galaxies is one of the things that I've been working on for a while. And so where do these Redshift 8 galaxies, are they all resolved? Absolutely not, but some of them definitely are. And so the green line is where the PSF from the Wide Field Camera 3 is. The drawback for Borg is that these are undithered observations. So since the spectrograph is staring into space, you cannot move the camera, and that means you are working with the native pixels. So it is really right at the edge of what you can resolve with WIG3. If you are, for instance, looking in candles, there everything is dithered. So basically the camera looks at a couple of positions, and so the sampling is a bit better, and so you can actually identify barely resolved sources a little better. However, this does seem to work. Back in 2015 with Richard, I worked on seeing if the effective radius could actually substitute for the H minus 3.6, so using a Spitzer color. And so these are IRAG red interlopers. So we found some interlopers and we looked at the sizes of Redshift 9, 10 galaxies. And it looks like, yeah, if you stick below 0.3 arc seconds, that seems to be a way to do it. Now, as you can see, this is not exactly a big sample, but it did hint at the fact that size might substitute for Spitzer color. And then as we keep finding these new Super 8s that we did confirm as Spitzer, you also see that they are where you expect them to be for sizes. So sizes have been used to confirm afterwards, and now we're going to see if we could actually use this as a substitute for Spitzer color. So I've been looking at this with all the Redshift sources that exist. So the Morishita 2018 result was another few Redshift 9 and 10 and one Redshift 10 galaxy from the Borg survey. The problem is that you have to look at this, and it's a distribution. It's not a single value. So the size distribution of galaxies basically follows a log normal at any redshift. And so the dashed line here in the histogram is the Shibuya 2015 distribution of high redshift galaxies at redshift 6. And the histogram is all the redshift 9 galaxies I could find. And well, they agree, but statistically they agree, but it does warn you against cutting it too close, because there is a tail towards brighter and bigger galaxies, and if you cut it too close, you start cutting the interesting stuff out, right? So that is, if you take a slice through that redshift, evolution, you get that histogram with the log normal distribution. Okay, so working further from that is that, well, we've got predictions for the luminosity function. So let's take the predictions from Charlotte and Mason in 2015 and turn them into a size distribution. What can I expect to see at redshift, 6 to 12 or something. The problem is that you then need to convert. You have to assume a size luminosity relation, and there's two basically. There's one from me from 2015, and there's one from 2012 from Grazian. And that's essentially, that one was for redshift 7, mine was for redshift 9. It depends, like both of them have different samples, so they end up with quite different size distribution that you can see in the bottom right plot here. So this is another way to visualize that. You take the actual observed size and the number of galaxies that you can see, and essentially extrapolate it until you run out of the entire volume of the universe at that redshift. Obviously, I'm a little partial towards my own, who isn't, but it does point out that if we apply a 0.3 arcsecond cutoff and simply cut off our selection that way, if the Grazian size luminosity holds, we're actually cutting off a good chunk of the brightest end of the luminosity function. If mine holds, there's no issue. So, but this is a word of warning, right? So it's well beyond m star for the luminosity function, but it's still, you're deselecting the brightest sources. Okay, I looked at the Morishita paper though, and you look at the visual rejections. Those are the green triangles, and the green upright triangles are noticeably all above 0.3 arcseconds. So it seems like if you want to not use a visual classification simply because you're going to have way more data than you can do that on, then perhaps a size cut or a size prior, where you essentially put a log normal on top of it, you weigh it that way, or just a hard cut, will get rid of a lot of the things that you need to visually identify. So checking how many of those do I then cut off if I actually use a 0.3 arcsecond cut in effective radius, and I assume my own, if I assume the size luminosity relation, depends a little bit on which one you use and which survey you're in. So really it's only a problem beyond redshift 10 because projection effect again. And it depends a little bit on where you want to be. So I was especially curious about Euclid wide, because that's another shallow survey. We can't follow that up with Spitzer. We don't have a ton of photometric points. So maybe size will help here. But you do start to throw away a fair amount of your data if you get beyond redshift 12 and you use a stringent size cut. However, if you do a more generous size cut, yes, you will still end up with contamination in there, but only in the case of the Borg fields will you reject some actual bona fide redshift galaxies. So that's the latest result on that. So it seems to be working just fine. You can actually use size for this. And another thing that I had my student Samir Kuzmish look at is you can use things like Gini and asymmetry, and they seem to be a little, said these things were a little fuzzy, right? So they're not exactly a PSF wide. They're a little fuzzier than that. They're got a little extra information. So we looked at the Robert Sporsani and the Joanna's Super 8s, and they are all a little off from where you expect point sources to be. This is only positives, and so this is not with all the possible contaminants in there, but it does point that these things might be a good alternative or additional information for morphology. So why are we doing that again? Okay, well, it's because Euclid and WFIRST are going to eat the sky in infrared, right? For a while, I had two versions of this slide, which is like, well, if I'm giving a European talk, I'm talking about Euclid, and if I'm giving a US talk, I'm talking about WFIRST. Essentially the same thing, right? You want to use morphology to select your higher redshift galaxies. Meanwhile, because none of this stuff is launched yet, I keep searching into other surveys. So there's a Spitzer Deep Wide survey, which has optical from the ground and near infrared from the ground from video. And so you can use color cuts, but there's no morphology confirmation just yet. And so the way that this works is that you've got these nebular emission lines going through both Spitzer fields. I'll actually run that again because this goes pretty quickly. So you've got these spikes going through both filters, and you see that the color changes quite a bit. And then I put the actual photometry points from Robert Bussani's 2020 paper and Stefano 2019 paper. And you see that all these high redshift sources at around redshift 8 do suggest strong nebular lines, but our models don't actually quite get there. So is that photometric error or not? That really depends on what the nebular line strength really depends on the kind of model that you're using. So for example, here I'm using BPAS models, and the same thing happens at around redshift 7 to about redshift 9. The colors go pretty red, but that doesn't mean they actually get to the redness of the IRAC color that we would expect. So there's something else going on. The models don't line up with the nebular emission line that the IRAC colors seem to suggest. So still work to do there. So the outstanding questions are, is the bright Lyman alpha emitters in the extended growth strip? Well, we checked with the Borg identified Super 8s, and they are confirmed with HEC Spitzer. Joanna did a great job, and then we went to do realty, GTC, and Keck follow-up. And so to what redshift do they occur? So I'll talk about the first one. I tried for every 8-meter class telescope that I could get my hands on. And so most of this was Keck work, because Keck is the one that usually confirms these. Here's my team on their observing trip, looking like really regretting that they had to go to Hawaii in the middle of winter. So the outstanding question was, is that only in the growth strip? Yes, looks like it. The preliminary is that there's no Lyman alpha in these Borg ones. So does it depend on Spitzer color? And that's the next question that we're trying to figure out. We got a little bit more, some of the last Spitzer time to find out if this is the case, because that means that the Super 8s in the growth strip are pretty unique. And that might mean that they're a very brief or they're a very atypical phase for reionizing sources. And so to what redshift does this occur? We're still collating the redshift 9, 10 targets, and it would be really interesting to see if we can get follow-up on those. Then, of course, we're looking towards the future telescopes. I don't have Lego models for WFIRST and Euclid yet, but I typically show Lego models if there's no actual data yet. And so we get a whole bunch of extra bit of information if we can get spectra from JWST. So we get things like what kind of star formation is actually happening in these things? What's the radiation field look like? What's the actual equivalent width of oxygen-3 rather than some assumed ratio? And so we can actually see the details of what's happening. And we get actually an actual redshift of the galaxy itself, not just the bubble around it. And so we'd like to do spectroscopy on these galaxies. There's 30 Doradus sitting in the center, pumping out UV photons. And on the redward line, we've got the emission line. And on the blue side, we were expecting to see absorption. So we'd like to see all of these things so that we can get an idea of how big the bubble is and what the geometry actually looks like. So, conclusions 1, Lyman alpha occurs within the brightest of galaxies. However, we're still looking at how common this is, but it looks like Guido Roberts Borsani actually found the 4 uncommon ones, but this is still in prep. The size of morphometrics of high redshift galaxies is a good constraint, and so that is going to be useful if you're going to do sky eater from space, and so you can pre-select high redshift sources that way, not just from their color, but also from their appearance, taking care to not throw away any additional information. Loose criteria for the sizes, but possibly also grouping them using morphometrics. So that's the first part of my talk. That's talk 1. And so this is all driven by high redshift searches. This is all driven by us trying to understand the high redshift universe. The thing is that if you're doing this, you're going to end up with this as well. You're going to accidentally survey the M dwarfs of our Milky Way. And so this was with two undergrads, Richard and Matt, our staff at Light Observatory. And so the motivation is that if you really are interested in those redshift 6 and beyond galaxies, even if they're resolved, there are still little red fuzzy things that are the dwarf stars in our own Milky Way. So all the way down in the main sequence, right, the M, L, T, and Y dwarfs float into your, astronomy is a windshield science, so everything is just in your field of view if you like it or not. And so these things are interlopers. We had the T naught. We had the T naught dwarfs earlier. And so since HSC sampling from Borg is a random sampling of the subsolar dwarf, it's actually really good to map the structure of our Milky Way in these ML and T dwarfs. It's not great. It's not an all-sky survey, but it is good enough because we're random sampling, again, because we weren't looking at the Milky Way. So the idea is let's identify the M dwarfs and determine what we can say about the shape of the Milky Way. And I've put Oscar in here because one man's trash, basically the rejects from one project can be the data for another project. So remember to root through the reject pile once in a while. So M dwarfs are these small, low mass stars. Typically, TRAPPIST-1 is one, but if we hear about them, that's, the news happens about the planets around TRAPPIST-1. They don't care about the planet itself, the star itself. And as we look at our Milky Way, we remember that the Borg fields really sampled a halo of our Milky Way. So the thick disk and halo pretty well. And since they're deep, especially for Milky Way kind of science, we do a pretty good job of counting their total number. So counting stars, it's a song and it's sometimes a bad idea. Because counting stars is the oldest technique that we've used, and it's also the way that we got the shape of our Milky Way wrong so many times. Fraught with issues, most of them are biases and conceptual gaps, and I am not, Kaptein is not alone in that, or Herschel. So most times the count rely on these giant stars, but really I'm now going to look for these low mass. They're still stars, M dwarfs, but at some point you're going to hit free floating or rogue planets. So the interest has definitely shifted to these subsolar stellar objects. So here's a Borg press release, and there's all the high redshift sources that we just talked about. And what we're interested in is that little bright star sitting in there. So there's a few stars just by pure accident in every field. Not a lot, like the statistics aren't great, but because we're looking at high galactic latitude, we've got 3 near infrared filters and 1 optical. That is nearly identical. That's nearly ideal to go find to find M dwarf stars. The near infrared color, the optical infrared color, might be a good way to subtype the M dwarfs. The L and T dwarfs, because they've got clouds and stuff, it gets really complicated. But if you find M dwarfs, they've got a fairly linear relation between type and optical infrared color. So how do I calibrate that? Well, let's stay within Hubble filters, stay within the same data sets. So calibrate that off the goods field using spectroscopically identified M dwarfs and spectroscopically typed M dwarfs. Identify the same thing in the near where you need to find them in the infrared colors, subtype everything using the optical infrared color, infer the distances based on the type and the apparent magnitude, and then say something intelligent about Milky Way structure, right? That's as far as my plan went. And so I started off typing them. These are all confirmed M dwarfs using GRISM spectroscopy. So we already knew what they were. I can actually identify their sizes. Again, I'm using the half-light radius, so I was doing that anyway. But now they have to be confirmed within those 2 dashed green lines because they have to be resolved. And their colors have to confirm with known M dwarf spectra. These are all M dwarfs from really close by, and I'm looking at, kiloparsecs away, M dwarfs. So that works. Yep, there is a color box for M dwarfs. There is a V minus J color dependence and type. So I can actually give a V minus J color, and then I get an M dwarf type. That seems to all work. With Borg, of course, the magnitude versus size relation is a little fuzzier thanks to the lack of dithering, but I can identify them. So there's my stellar objects. I identify the ones that are in the M dwarf box, which is the blue one, and then I have a bunch of questions, right? So step 3, profit. And so what's the typical scale height for M dwarfs? Because we didn't know it for now up until then. Is there a north-south discrepancy? Because Nor Pearskull in 2009 did this for the goods now north and south fields with his confirmed M dwarfs and said, well, I'm seeing more M dwarfs in the north, and I should be seeing more M dwarfs in the southern sky because we're a little above the galactic plane. And is there any evidence for a halo or secondary component, right? I haven't actually said anything about that yet. So typically I nearly gave up on this project because I found, between 0 to 5 M dwarfs in each rhythmic 3 field. And then there was one with 22. And I figured that my identification had just failed spectacularly, and I was accidentally sweeping high redshift sources into my M dwarf count. So I figured, well, this is nearly it. Thankfully, always check with your friends. So this field put a lot of those M dwarfs at 25 kiloparsec. So that was another thing that was a bit weird. And so if you check with your friends, especially if they know the Milky Way really well, they'll say, oh, that's a Sagittarius stream, don't worry about it. It was at the right distance, it's the right density, and the fun thing is it's 10 times the contrast as SDSS. So if you are going to do an all-sky infrared survey to these kind of depths with an HST-like instrument, if you're Euclid or W first, you're suddenly going to have the Sagittarius stream stick out at 10 times the contrast that you saw it in SDSS, because there's just simply more M dwarfs to play with. And we're going to pick them all up. So that's going to be pretty cool in the eventual data. So you've got distances, you calculate the height above the plane, so you get below and above the plane, and with every M dwarf type, you kind of see that, the M8 are the faintest one, so I only see the closest one, and by the time I get to M0, they go all the way out to 30 kiloparsec. So there's definitely a secondary component. There's something that looks like the thick disk, and then there's a secondary component of some kind. So that was exciting. We tried to fit vertical profiles, failed horrendously, so I could just kind of give a good guess for what the average vertical scale height was. And it doesn't seem to be correlated with subtype, but I couldn't really tell. There does seem to be that north-south discrepancy seem to be still there, and I can definitely detect the halo or thick disk. The Sagittarius stream, at least, is a halo component, and that was definitely there. So cool. Now enter these two. This is Diwitje and Isabel, and they were my students, and I said, well, I have this catalog, and I hear MCMC is a good thing. And that was about the level that I was at, because I was still learning this myself. And I thought, well, you know what? Maybe we can do a little better just using this new technique. And here's my catalog. Can you figure this out using MCMC? And this is one of those wonderful things that happen to professors or more senior people. You give a problem to smart young people, and they just run away and come back 2 weeks later and just kind of like, oh yes, well, we've changed the optimizer, and suddenly they're the experts. And so I learned more from them than the other way around, it feels like. But they ran MCMC on the exact same catalog, but they tried a disk-only model, and they tried a disk and halo model. And the good news about MCMC is that you can identify where things get degenerate, and you can see, you get error bars that if they're not Gaussian, because your sampling function is just bananas, because again, this wasn't meant to do this at all, right? It's just random sampling, but it's also all kinds of shallow, different depths, and we're all different directions. So you can see that not everything is perfectly Gaussian. But they found the disk, the thickness of our disk, the power law of the halo and the oblateness of the halo. So they actually constrained quite a bit from randomly found M dwarfs. In fact, they constrained the vertical scale height to about 300 parsec. That means if you count their entire model, if you sum everything together, that's 58 billion M dwarfs, which is about right. It's about a quarter of all the stars in the Milky Way. And the neat part is they also found how big the halo component was. And 7% of them are in the halo, which means that the halo component, and look at the number of points we have here, right? This is the number, how big is your halo relatively to your stellar mass. And the stellar, this is the stellar halo, it's not the dark matter halo. This is how many stars you got free floating in a ball around your main galaxy, what we think of as the galaxy. And so we had a point for the Milky Way from Stéphane Couteau, and we had about 6 points even for other galaxies. And so the fact that they got this out of my 274 M dwarfs with their model with error bars is pretty good for a couple of bachelor students, I would say. So that appeared in 2016 under both their names. They're equal contributors, by the way. They were fantastic collaborators. So I love the fact that this is their plot, and I can actually show that the red line is what you expect for a lambda CDM. So whatever the Milky Way is doing, it's pretty much doing what you'd expect for lambda CDM. As soon as you get lower than the Milky Way, you actually get problem children like M101 with from document 2014, and we now are filling in this plot. But the fact that we got one for the Milky Way was pretty cool. So the next thing up is that we are going to double and double again our number of sightlines with Hubble, so we can add more parameters to our MCMC project. So we can do things like we can leave the position of the sun actually not fixed, but leave it loose, because let's see where the M dwarf disk keeps our, with respect to where our sun is with respect to the disk of M dwarfs. We can leave the scale length of the disk free. We can hopefully, and this is something that I sincerely hope to do, get a handle on the brown dwarf subtype, and I'll get to why. And maybe we'll add a thick disk or a bulge or a broken power law halo. Like there's all kinds of free parameters that you can start adding, but it's pretty neat that you can actually constrain the Milky Way shape this way. The reason that I want the M dwarf or the M and L and T dwarf subtypes is that we've been trying to get the vertical scale height for subdwarf for these like low mass stars for a while. This is everybody's data points, but we haven't pushed well beyond L naught. And there is a, from Ryan 2017, there is a prediction that if dwarfs cool, which they do over their lifetime, but their population gets kinematically heated, you should see the effects of basically the slope of the star formation history of the Milky Way as a vertical profile, change in vertical profile for their subtype with subtype. So this would be a way to do galactic archaeology by using different subtypes of stars, watch them cool, and kinematically heat the population, so throw more out of the disk, and see if this prediction actually holds. So very, very curious about this. It would be very neat to get better numbers on, especially the L and T dwarfs. So that means lots of lines of sight and maybe a better handle on getting the subtype out of a broad color. That is tricky, but it is possibly doable. So this conclusions number 2, just the Milky Way. We have an M dwarf catalog. We found the Sagittarius stream again, but hey, I found it again. And the MCMC works so much better, and we actually found a fantastic result there. And so we'll double the number of fields and double it again, and then we expand to L and T dwarfs because we finally have the numbers there then. So redshift galaxies, Lyman alpha search, morphometrics will get you hopefully cleaner samples of redshift 8 galaxies, and oh, look at that. While you're at it, you're ejecting things that in a good part are going to be subsolar stars, subsolar mass stars, and you can do interesting science with that one of those rejection piles. So use all the data. That's basically what I'm doing here. And if you have clever people to work with, then that becomes quite a joy to do. So that would be the talk. I think I kept within time just yet. Yes, perfect. So I'll take questions.
I'll do the collective applause. Thank you so much, Benne. That was super interesting for a couple of reasons. Indeed, let's open the floor for questions. Please use the raise hand feature, or if you prefer, just fire it in the chat window, and I'll curate that. Doug, you're on the spot.
Hi, it was a wonderful talk. Very quick question for you. Why do you think Stefan Courteau's data point was so low? So what is it that really added so much here? Because that looks like a real change.
Okay, so logarithmic axes. So I don't have an error bar on that Milky Way halo fraction, but it is essentially 1%, 1 to 2%. From his result, and our error bar is goes from about, if I remember correctly, goes from 0%, or is it 3%? I can't remember quite, but it is quite a wide error bar. That's a wide error bar, considering it's a logarithmic plot, right? So
yeah, you're right.
And it's asymmetric. So it is more, it's a better upper limit than it is a lower limit. So we don't disagree with Stefan's result that much. It is based on giants versus MDORs, right? So
well, that was what I was curious about. I was curious about whether you thought that you actually had better leverage by going to the M dwarfs. That was exactly what I was curious.
Well, then I have to invoke the initial mass function, and I don't know what that looks like at the M dwarf level, to be honest, right? So this is our model for the disk, saying this is the disk to the halo ratio, right? Maybe it goes down a little bit if you add a bold. So I don't think we're actually in that much disagreement. It was just really cool that we got this. Yep. So that was pretty neat. Thanks for the question.
Thanks.
And I presume with the upcoming Borg 2 and 3 that will improve the model at least somewhat.
Yeah, I'm always curious where the gain happens, right? So the gain could happen that suddenly where we can do subtype, for example. That would be great, but the actual individual points would still have this error bar. Or, I mean, our assumption is that the scale length is the same as it is from, where do we get that from? Lamost, I think. So you do assume certain things, and so maybe we can start freeing some of the fixed parameters first before I start really hammering down the error bar and essentially deceive myself. So I think the assumptions that went in were quite reasonable, but first thing I would let go would be the scale length to see if that was the same. And then, yeah, I think we'd also look for differences in, for instance, early versus late type MDORs, that kind of thing. See if there's a difference.
Mm-hmm. Any other questions? Oh. There's one comment from Nyenka that background galaxies are apparently annoying too. I personally tend to disagree, but you know, we need all perspectives on this. Well, other questions are being thought of. I have a bit of a practical question, and I hope I don't telegraph my follow-up. Were you planning on this this kind of double whammy when you were doing the Super 8? Proposal, or was this just completely serendipitous?
This was, okay, so the origin from this is that I was doing star-galaxy separation for my thesis. And so thinking about how I can identify point sources versus anything that's a little extended was something that was ongoing. Michaela and I were just chatting, and I was asking him about, you know, what his main headache was, and that was, yeah, it's these M dwarfs. They seem to keep sneaking in. So that's when I started thinking about whether or not you can use the Borg survey to do Milky Way science. But that was an idea that we kind of batted back and forth in 2007, and I didn't actually do anything with it until 2014. So yeah, it is. The ideas take a little while to percolate sometimes, especially if it's archival. But the fact that we got a wonderful undergrad project out of it really tickled me. So
yeah.
I think I try to think of new ways to use existing data, and this was definitely on the list of, well, what could you do with it? What can you do with your main annoyance, really?
So following up on that, with the future Borg expansion, have you tried to incorporate that, and has that modified your observing strategy at all, or are you just sticking with a completely random best kind of?
They're pure parallel meaning that whenever COS or STIS, whenever one of the two spectrographs is busy, that's when we can, that's an opportunity with the pure parallel observations. The filter strategy has changed a little bit, and that makes it a non-homogeneous sample. And so it will be really tricky to put everything together. So they're varying depth, because the depth is set by the main observation, by the spectroscopic observation. So again, you have to fit your parallel exposures in there. And so you have different depths, and you have slightly different optical filters. We switched optical filter and we added another infrared filter. So that suddenly changed the landscape again. So it's a very inhomogeneous survey in that respect. But you can, it is all HST data, which is wonderful. And so MCMC is actually really good at taking that into account, right? So if leaving that open is a good way to do it, because let's see if I can find it here. There's if you do all the variables here, we've got a central density, we've got a fraction that's in the halo, that's that 7%, and then there's an F all the way at the end, which I think the students call it the fudge factor, but it's essentially the amount of contamination or issues that you're having in the data. And Borg has a high fraction of chromie data or bad identification. These are photometrically identified stars, so you do have you will have to deal with noise in your data. So there's noise in this model. And it's perfectly acceptable because it's a 2-component model for the Milky Way, which is definitely not bad. And so hopefully we can beat that down a little bit. I think that's really where the multiple lines of sight become very helpful. The random sampling allows us to do this. You wouldn't be able to do this with just a big field. We see that because candles are a few big fields, and the counts there are much less constraining to the overall Milky Way's shape and size. So, if you're looking for, I know Nika looks at nearby stars for, what is it, planetary disks, and so if you're looking for planets, you're always picking up M dwarfs behind you, so you can actually start calculating what your odds are that that thing is an M dwarf if you know what the totals are. So if you know how many M dwarfs there are in the Milky Way, then here's my predicted probability. So
very cool. Thank you so much again. I'll give a few seconds in case anyone has some last minute comments or questions or answers.
I did blast everybody with a lot of plots and information. There was a lot to figure out here, and yeah, you can learn a lot from just a few Milky Way. A few HST pictures. So it'll be pretty neat to mine this data for some time to come. Another thing that I want to do is actually see if I can identify the M dwarf types. So model the whole thing with machine learning, for example, and see if my predicted machine learning for the high redshift sources agrees with the highly qualified observers visually identifying these things. So let's see if we can improve our technique for high redshift selection, because it's very much color plus visual identification. So anything that we can do on top of that would be useful, because Euclid is going to do 80% of the sky, and so suddenly we have this information on 80% of the sky, and you can you can't do that to a student, right? You go like, hey, go visually identify every single source in the Euclid catalogs. And so that would be something where we can data mine that and look for high redshift sources and see how the universe evolves at redshift 20 to now. So.
Oh, very, very cool. And definitely a nice step towards the future. Well, thank you again. I'll give one final communal round of applause. Thanks again for your time, and I guess we'll leave it at that.
Sure. And if anybody thinks of something, feel free to hit me up. And yeah, thanks for having me.
Yeah.
I look forward to coming in person one day.
Absolutely. Thanks again. Stay safe.
Cheers.